Imagine a world 2.5 billion years ago, a planet in metamorphosis, a geochemical cauldron where biology, tectonics and atmosphere negotiated a new equilibrium. This is the Siderian, a chronometric slab in deep time, 2,500 to 2,300 million years before present, 200 million years during which iron bled from ocean to rock, oxygen escaped its microbial prisons, and ice advanced and retreated under an atmosphere being rewritten. In this narration I will follow the threads that make the Siderian singular, the banded iron formations, BIFs, that give the period its name, the tectonomagmatic pulses and large igneous provinces, the Great Oxidation Event and its climate feedbacks, the Huronian Glaciation episodes, and the marine and biogeochemical shifts recorded in isotopes and minerals. This is a ledger of numbers, isotopic ratios, depositional geometries and the slow fury of life changing a planet's chemistry. It is a ledger written in stone. Begin with etymology and convention. Siderian, sideros, iron. The period is defined chronometrically, not by a GSSP. Its boundaries are anchored by absolute ages rather than a single stratotype. Ratified in 1990, the Siderian stands as the first internationally recognized period of the Proterozoic. Its lower boundary coincides with the surge of extensive iron deposition. Its upper boundary sits at the transition to the Rheation. Alternate names have been proposed: oxygen iron, highlighting the atmospheric transition, Scorian, as a stratigraphic alternative. But sideros remains evocative, billions of tons of iron, precipitated from seawater, forming layered magnetite and hematite, recording the interplay between microbial oxygen production and ocean chemistry. Banded iron formations dominate the early Siderian stratigraphic record, especially in the Karpval and Pilbara cratons. These BIFs are more than pretty banding. They are time-stamped chemical reactors. Their iron oxyhydroxide and magnetite layers grew as oxygen produced by anaerobic, photosynthetic microbes, Cyanobacteria early in their evolutionary experimentation, oxidized ferrous iron, Fe2+, in seawater to ferric iron, Fe3+, which hydrolyzed and sank as insoluble iron oxides. Fluxes. Think of dissolved oceanic iron inventories on the order of hundreds to thousands of micromoles per liter in the Archean oceans being titrated to near zero in shelfal settings by pulses of oxygen. The early Siderian pulses of deposition peaked between roughly 2,500 and 2,450 Ma, synchronous with volcanic and rift-related sedimentation in multiple cratons. The Shiva, Kuraman, Penge and Dorridale formations are local names. Globally, the phenomenon is coherent: iron removal, layered deposition, and the visual transformation of seas from greenish, iron-rich fluids to clear, oxygenated waters as the ocean's oxygen sink became exhausted. This exhaustion of oceanic Fe2+ set up one of the biggest inflection points in Earth history, the Great Oxidation Event, GO. From proxy data and mass balance constraints we see a jump in atmospheric Po2 by at least 104 times baseline, from the order of 10⁻⁶ bars to is greater than or equal to 2 times 10⁻³ bars between approximately 2,410 and 2,320 Ma. That increase is not merely a number. It reflects a systemic shift where biogenic oxygen production overcame the aggregate reductant sinks. Volcanic reduced gases, ferrous iron in seawater and crustal materials, and reduced organic carbon burial at flux balances compatible with new steady states. The oxygen rise is documented by the disappearance of mass-independent fractionation of sulfur, MIFS, at approximately 2,322 plus or minus 15 Ma, by the increase in delta 56 Fe in seawater towards zero or positive values, and by the isotopic fingerprints in sedimentary sulfides and carbonates. The GO is a planetary phase transition. The biogeochemical choreography is intricate. For most of the Archean, ocean chemistry was dominated by ferruginous conditions, low O2, high dissolved Fe2+, and anoxic deep waters. The Siderian begins with vast reservoirs of reactive iron. Cyanobacterial oxygen production in shallow photic zones oxidized that iron, magnetite and hematite precipitated, and formed the rhythmic laminae we now mine for iron ore. But once the reactive iron reservoir declined, oxygen began building in the atmosphere. Atmosphere-ocean redox feedbacks then altered the greenhouse balance. Methane, previously at high partial pressures sustained by methanogenic communities under reducing atmospheres, was oxidized by the increasing O2 and by photochemical processes, decreasing its lifetime and partial pressure from estimates of hundreds of ppmv in the late Archean to a few ppmv in the early Proterozoic. Methane levels are estimated to have dropped from roughly 300 ppmv to 4 ppmv, a dramatic reduction with commensurate radiative forcing implications. CO the 2nd of May have adjusted to a new equilibrium, perhaps around 1.1 times 10⁻² bars, buffered by silicate weathering feedbacks and volcanic degassing. The net radiative loss precipitated deep global cooling, the Huronian glaciation systems. The Huronian glaciation complex is a critical Siderian era climatic response, spanning roughly 2,450 to 2,200 ma with episodic pulses. 3 of its 4 recognized glacial intervals fall within the Siderian. The glaciations are recorded as diamictites, dropstones, rhythmites and cap carbonates across multiple cratons, Wyoming, Karpval, Laurentia and Karelia. The oldest Siderian glaciation, circa 2440–2420 ma, appears in the Deutschland Formation and correlates with the Campbell Lake and Headquarters Quartz units. The Magdalena event, circa 2380–2360 ma, is marked by cap carbonate sequences above the Bruce and Wagner's, and a later Siderian pulse, circa 2340–2310 ma, is represented by the Gauganda Formation and Wright-Fontaine diamictite. These were not minor advances. Paleomagnetic and sedimentary indicators suggest continental-scale cold, possibly including low-latitude glaciation. Whether any of these events reached a full Snowball Earth state remains a subject of debate, but the thermodynamic consequences of a methane collapse and CO2 buffering certainly allowed large-scale glaciation to occur. Tectonics and magmatism provide the backdrop and the drivers behind many Siderian processes. The epoch saw growth and reconfiguration of cratonic plates, pulses of lip activity, and the incipient breakup of a putative supercontinent, Kenorland. Dike swarms, Mistocene, circa 2470 ma, Metashawan, 2470–2450 ma, Scory, circa 2418–2375 ma, Widgimoltha, circa 2410 ma, and others, defined huge thermal and magmatic events that remobilized lithosphere and regolith. Mistocene and Metashawan have surface areas greater than 100,000 square kilometers and greater than 300,000 square kilometers respectively, placing them among the archetypes of early Proterozoic lips. These intrusions correlate in time with rift-related sedimentation in the Hurwitz Basin, Transvaal and Pilbara basins, and with depositional unconformities and transgressive-regressive cycles recorded in supersequences such as Brockman, 250–2449 ma, Wangara, capped at 2449 ma, and Taree Creek, 2449–2410 ma. The timing and footprint of such magmatism modulated atmospheric composition by modulating volcanic degassing fluxes, CO2, SO2, H2S, and by providing reactive substrates that influenced oxidative weathering rates on emergent land. Kenorland's breakup around 2450 ma, initiated primarily in Laurentia, created extensional basins and contributed to the sedimentological diversity of the Siderian, Huronian supergroup sandstones with arcosic, feldspathic and quartzose components, snowy pass quartzites with marble and phyllite interbeds, rhythmite and dropstone successions in the Hurwitz group, and the thick Transvaal supergroup sequences in South Africa, shales, sandstones and siltstones interleaved with BIFs and volcanics. The Brockman supersequences BIF and mudrock packages, the Wangara rhyolites and dolerites, and the Teree Creek sandstones and limestones together document fluctuating sea level, volcanism and weathering regimes tied to tectonically driven accommodation space. Marine geochemistry during the Siderian records the redox flip in high-fidelity detail. Iron isotopes shift. Delta 56 Fe values increase by up to approximately 3 per mil relative to Archean baselines, indicating a change from extensive dissimilatory iron reduction to environments where iron oxide precipitation dominated and seawater isotopic compositions became less negative, approaching modern values with delta 56 Fe generally greater than -0.5 per mil. This isotopic shift accompanies the reduction in ferruginous deep water influence and an increase in sulfide precipitation via bacterial sulfate reduction. Sulfur isotopes show pronounced fractionations. Delta 34S excursions and the disappearance of MIFS indicate oxidative weathering liberated sulfate to the oceans, enabling bacterial sulfate reduction to generate large fractionations. Yet seawater sulfate concentrations remained modest relative to Phanerozoic levels, 1 to 2 mm versus the modern approximately 28 mm, a constraint that keeps the system partially limited. Significant sulfur cycling, but not at modern magnitude. Carbon isotopes during the Siderian add nuance. Bulk carbonate delta 13C values remain near 0 per mil in several sequences, Mount Bruce, Transvaal, Huronian, while organic carbon delta 13C hovers near -28 per mil. These near-constant values imply a steady-state carbon cycle where sources and sinks balanced over long periods, but they do not imply stasis. Instead, they cloak dynamic fluxes, enhanced oxidative weathering delivering nutrients, phosphate, and oxidants to the ocean, volcanic inputs replenishing CO2, and evolving biological sinks varying locally as cyanobacteria expanded their ecological reach. The most dramatic local carbon signals, very negative delta 13C values in the lower Timeball Hill Formation, are interpretable as fingerprints of localized sulfate reduction and organic remineralization entangled with capped carbonate deposition after glacial termination. Life in the Siderian is both familiar and alien. Cyanobacteria diversify into filamentous forms like Pseudanobina, developing intercellular molecular communication and chain morphologies that improve vertical positioning in the photic zone and possibly community resilience against environmental perturbations. Microfossils in black chert from the Teree Creek group, approximately 2,450 ma, and cyanobacterial remnants in the Kuraman Iron Formation preserve morphological evidence of microbial mat communities. Stromatolites proliferate and begin to diversify taxonomically by approximately 2,330 ma in the Fennoscandian Shield. Early eukaryotic signatures like those attributed to Giardia emerge near the tail end of the Siderian, approximately 2,309 ma, though these assignments are debated and rest upon morphological and molecular clock inferences. Regardless, the Siderian hosts the microbial innovations that drive planetary-scale oxygenation. Sediment-hosted metals, or proxies and economic geology also flower in these times. The Transvaal and Griqualand West basins record hematite, magnetite, marl, greywacke and hyaloclastite, a mineralogical spectrum tied to iron and silica cycling, hydrothermal inputs and shallow marine dynamics. Trace metals, early gold, uranium, aluminum anomalies, appear in Huronian and Snowy Pass successions. Low sulfidation copper and nickel deposits form in rifted terrains within Nina and Kalahari cratons as mafic magmatism and hydrothermal systems exploited extensional architectures. These deposits are not just economic curiosities, they were reactive sinks and potential nutrient sources shaping early marine chemistry. Isotope chronometry pins many Siderian events with precision. Dike swarms are dated to the 2470-2410 Ma window, with Metashawan and Mystacini at ~2470-2450 Ma, Scory spanning ~2418-2375 Ma, Wiji-Multha at ~2410 Ma, and Sabanga Port at ~2408 Ma. Sulfur MIF termination at 2322 plus or minus 15 Ma constrains the onset of a sustained oxygenated atmosphere. The GO oxygenation window, 2410 to 2320 Ma, overlaps with the cessation of most major BIF deposition in many basins and with the appearance of glacial diamectites that mark the Huronian pulses. These constraints allow a relatively tight coupling of redox, climate and tectonics across a few tens of millions of years within the Siderian's 200 million year span. Consider the feedbacks as a systems engineer. Reactive iron in the ocean represents a massive oxygen sink. Cyanobacterial oxygen production rates increase as nutrient supply, particularly phosphate, allows higher primary productivity. Rising O2 oxidizes methane and Fe2+, removing greenhouse warming and iron reservoirs respectively. Climatic cooling follows. Glaciation alters weathering regimes, increasing physical erosion and eventually delivering cations for CO2 drawdown via silicate weathering when deglaciation occurs. Cap carbonates form during transient overshoots in alkalinity and CO2 drawdown. The Siderian therefore is a demonstration of coupled nonlinear Earth system behavior where biological innovation acts as a forcing, and geology provides inertia, reservoirs and feedbacks. Paleogeographically, the Siderian world is fragmented yet coherently active. Cratons such as the Superior, Pilbara, Karpval, Kola Karelia, North China and Wyoming display synchronous depositional and magmatic records. The Transvaal supergroup's lower half, deposited throughout the Siderian, preserves an archetype of shallow marine to continental transition sequences, patterned shales, sandstones and siltstones interleaved with BIFs and volcanogenic sediments. The Hurwitz group's rhythmite and dropstone records of 2450 to 2110 Ma capture glacial dynamics over a protracted interval. While the Huronian supergroup's archosic sandstones, conglomerates, limestones and gold-bearing horizons record sediment provenance, transport mechanisms and basin evolution during and after Kenorland rifting. If one seeks a metaphor, the Siderian is the planet's exhalation of oxygen after a long-hold breath of reducing conditions. It is not a single event but a prolonged exhalation with hiccups, BIF deposition peaks, oxygen rises, methane collapses, ice advances, a series of pulses imprinting a new regime. Rocks archive this transition in layered iron, in sulfur isotopes relinquishing MIF signatures, in delta 56 Fe approaching modern-like values, in episodic diamectites and cap carbonates, and in microfossils preserving the microbial agents of change. As an epilogue to this epoch, consider the legacy. The oxygenation pathway initiated in the Siderian set the stage for subsequent redox evolution through the Proterozoic, including transient oxygenation events and the later Neoproterozoic Snowball Earth episodes. The exhaustion of iron reservoirs freed oxygen to reshape surface environments and biological possibilities. Mineral deposits formed then continue to constitute modern economies. Iron ore belts are direct material legacies of microbial chemistry and tectonic subsidence 2.5 billion years ago. In the final calculus, the Siderian is a crucible where life, lithosphere and atmosphere co-evolved. It is a story told in isotopic shifts, in the spacing of laminae, in dike swarm geometries, in supersequence architectures and in the stoichiometry of redox reactions at planetary scales. Its numerics, ages, PO2 increases of is greater than or equal to 104 times, methane declines by 2 orders of magnitude, seawater sulfate at 1 to 2 mm, delta 56 Fe shifts up to 3 per mil, are not mere trivia but the quantitative scaffolding of Earth's early oxidation. The creative spark lies in reading these numbers as the signatures of processes, cyanobacterial oxygen factories, magmatic throes, continental splitting, ocean chemistry titrations and climatic catastrophes and recoveries. Listen to the rocks. Banding that alternates ferruginous and siliceous laminae is a fossilized oscillation between oxygen pulses and iron supply. Cap carbonates are the breath exhaled after glacial suffocation. Sulfur isotopes speak of atmospheric thresholds crossed. Dike swarms record heat pulses that set up basins and nutrient fluxes. The Siderian is not just an age. It's a planetary experiment in feedbacks, thresholds and the novel agency of life. The narrative embedded in its strata is both poetic and precise, a machine like Earth that, under the influence of microbial metabolism, moved irreversibly toward an oxidized surface world.